Let's now look at convolutional neural networks in detail. So there are many different convolutional neural networks. The first one here is called the LeNet, and it was proposed several decades ago. So basically, it is convolution followed by subsampling, another convolution followed by another sampling, and then followed by two fully connected layers, and then the output layer. So this CNN is the AlexNet, which we have seen in last lecture and this lecture earlier. And this one is called VGG. So it is a group in VGG is a group in Oxford. So this is even deeper in the architecture. And here you can see the labels of different kind of layers. So we will start with simple structures to see how convolutional neural networks work. Let's start with a fully connected layer. Suppose we have a color image of size 32 by 32 times 3. 3 is for the channel of RGB. And to use a fully connected layer on this image, we need to stretch it into a vector of size 3072. I suppose our next layer has 10 units, 10 hidden units, so 10 activations. Then we need a weight matrix of size 10 times 3072. So we need so many ways to map input to this hidden layer. So here, each number is a result of taking a dot product between a row of W and the input X. So we do it 10 times and have 10 numbers. So that is a fully connected layer. And when we use a convolutional layer, we do not do that kind of stretching or vectorization. We use its natural tensor representation to preserve the spatial structure of an image. So a color image is represented as a tensor of 32 times 32 times 3 over here. And suppose we have a filter of spatial resolution of 5 by 5. And because we are convolving with a color image, so we need a third dimension of 3. So this dimension here, 3, need to be always extend to the full depth of the input volume. That is, this number must match the number of input channels. And then we will convolve this filter with the image, slide this filter over the image to compute the dot products. So here is one of the operation where we use this 5 by 5 times 3 filter to convolve with a region on the input image of the same size. And we do produce an output by taking a dot product between the filter over here and this 5 times 5 times 3 sub-image on the input. So that is basically a 75 dimensional dot product. And we also need to add a bias. So this will produce one output. And after we do this across all the image, slide through all the image, so each slide will generate a number. And after we slide over all the locations, what we have will be 28 by 28, we call this an activation map. The size is 28 by 28, and we have only one channel. And suppose we have another filter. Here we use a green color to represent it. So if we have a green filter, our first filter suppose it's blue, and the second filter is green. And then we do this again, slide over and do dot products. We will have another activation map of the same size of 28 by 28. And suppose we have 6 of such filters of 5 by 5 times 3. Here we don't always write times 3 because you must have that times 3 to match the input channel. So we will get 6 separated activation maps over here. And then we stack these up, then we will get a new image of size 28 by 28 by 6. We call it image with a quotation because it's not visually recognizable images over here. Then let's look at the convolution. And if our input has a size of 7 by 7, and if we have a 3 by 3 filter over here, then during convolution, we do a dot product, and then we slide over to the right by 1 pixel, and we compute another dot product. And after 3 more such sliding and dot products, then it comes to here. And then it will, in the next slide, it will move down and up to here. And after we do all this sliding, what we have is a 5 by 5 output. And if that is basically the default with a stride 1. If we have a stride more than 1, we will do convolution with stride, suppose stride of 2. Then the first dot product is still the same, but in the second, we move by 2 pixels to up to here. After we do all the sliding, and when we move down, we also move down by 2 pixels. Then what we have will be a 3 by 3 output. It's much smaller. So here's the question. So can we convolve this 7 by 7 input using a 3 by 3 filter with stride of 3? Actually, it doesn't fit. Unless we cannot apply this 3 by 3 filter on 7 by 7 input with a stride of 3 unless we ignore part of the image. So here, actually, we can figure out a formulation for the output size. Suppose the input size is n by n, and our filter size is f by f, and the stride is the size of our stride. And then output size has this formula, n minus f divided by stride plus 1. So in our previous example, n equal to 7, f equal to 3. So if we have stride of 1, that's a default, then the output will have a size of 5 by 5. And if our stride is 2, our output will have 3. But if we have a stride of 3, this we will not have an integer, instead we have a float number. So it cannot be applied unless we ignore part of the image of 7. So another operation is zero padding, right? So suppose we still have the same 7 by 7 image and 3 by 3 filter, but now we apply with a stride 1 and pad it with 1 pixel along the border. So here we pad the 0 along the border of the 7 by 7 image. What will be the output? So actually what we have will be still a 7 by 7 output. So this is very common. In general, we will do if we see a convolution layer with stride 1, filter of f times f, then we will do a zero padding with f minus 1 divided by 2. And this will help us to preserve the size spatially. That is, your output will have the same size as your input. So when we have a filter of 3 by 3, we do a zero padding of 1 0 on each side. And if our filter size is 5, we pad 2 zeros on each side. And if we have a filter of 7, we pad 3 zeros. Without padding, we can see that the convolution will actually shrink our image. If our input is 32 by 32, if we can repeatedly convolve it using 5 by 5 filters, it will shrink the volume spatially. And after the first convolution, suppose we have 6 5 by 5 times 3 filters, then this will be the size of 28 by 28 with 6 channels. And if we convolve it again with 10 5 by 5 times 6 filters, this 6 must match the channel here, 6. Right? And then what we have will be a 24 by 24 times 10 output channels. So this will be shrinked by another 4 pixels, 4 units along each side. Two on each side. So basically it's reduced by 4 in row and column. So here is an exercise. So if our input is still 32 by 32 times 3, so it's a color image. Suppose we have 10 5 by 5 filters. Notice here I didn't write times 3, right? Because you have to times 3 because your input channel has 3 channels. So we do not always write out times 3. We stride 1 and pad 2. This is the pad means the zero padding of 2. So what is the output volume size? So now please pause the video and do your computation. And this is how we compute it, right? So because the original size is 32 by 32, so this is n, but we do zero padding. So after you pad 2 zeros on each side, so basically it becomes 32 times 4, that is 36 times 36. So this is n minus f, that is the filter size of 5, and then we divide it by stride, which is 1, and then plus 1. So the output is 32 spatially, right? So that is, we still have the same size of 32 by 32, but now with 10 output channels. Another exercise. What is the number of parameters for this layer? So please pause the video and try to give your answer. So here is the answer. And here we have each filter will have 5 by 5 times 3, right? So remember I said here we said 5 by 5, but actually it's 5 by 5 times 3 because we have to have 3 channels to match the 3 input channels, right? So we have to, even if we don't explicitly write 3 times 3 over here, you still need to consider it, right? So that's a little bit tricky. So we need to compute. So each filter we have 5 times 5 times 3. So many parameters, right? So many weights. And we also need to have a bias, so that we need 1 parameter for the bias. So each filter will has 76 parameters. Since we have 10 filters, we have 76 times 10, that is 760 parameters. Another very popular layer is called pooling layer, and its function is to do downsampling. The objective is to make the representations smaller and more manageable. So it's kind of dimensionality reduction. So it will operate on each of the activation map independently. For example, here we have a 224 square input with 64 channels. And if we are doing pooling, we do it on each of the activation map, that is each channel separately. So we will reduce the size of the image, but not the number of channels. Right? The number of channels is still 64, still 64 over here. Right? So this is an example. For example, this is it's more like an ultrasound image, and we do downsampling. That is basically we ignore every other pixel, right? So we have a much smaller image over here. The most common pooling is called max pooling, right? So there's also mean pooling. In max pooling, we use for example, with a 2x2 filters with stride 2, then we use this filter to compute the max for this 2x2 region, right? So 2x2 defines how large the region we consider, and max pooling means we take the maximum value in this region, right? And we do, in this example, we do it use a stride 2, right? Stride 2. Therefore, your first max pooling is over here. Then the next max pooling we stride by 2, so it's over here. And this is fourth, and this is third and fourth. And after we slice through all the image over here, what you have is just the maximum in each of these colored subregions. These 6, 8, 3, and 4. So this is max pooling. So that's all the important layers that we need for build a standard convolutional neural network. And in your lab, we will build such a convolutional neural network. So here are the definition of the architecture, and you can see convolution. This is 2D convolution, the max pooling, and this is a linear layer. Linear layer is a fully connected layer, right? So that is a definition of different layers over here. And in the forward, in over here, it defines the architecture. For example, you do convolution first, then do a ReLU, and then do a max pooling. Right? So this is another convolution. And this is flattening or vectorization or stretching. And this is the fully connected layers followed by ReLU. Right? So that is the forward path defines the architecture. Right? So in the notebook, I have analyzed one example in detail. For example, if the input image size, so here, there, right? So in the PyTorch, we write the channel in front, right? So the number of channels, this is the image size, right? So after the first convolution, the size we have will be 6 times 28 by 28, because here this 5 is the kernel size, right? And 6 is the output channel. Then after max pooling, this is reduced by half to 14 by 14. And then we do another convolution, still with a kernel size of 5. So we have 5 by 5 over here. This sorry here, right? So here is a 5 by 5. After the convolution, we have 10 by 10, and then we do a max pooling, we have 5 by 5. Then we move on to the fully connected layers, and finally to the class label as a final output layer. Right, so that is, we will explore it in the lab. Again, this lecture has used many materials from many other top researchers. And here are some references that you can go deeper. And again, the PyTorch documentation are very useful. And our lab also contains some references, right? So next I will move on to the lab notebooks, and we will give some feedback in the end of the week. Okay, that's all.